has frequency distributions, group frequency distributions, stem leaf plots. And how will we sort of summarize our data and present our data using, in this case, graphing plots, some way to graph the data. And so the latter part, meaning sections 2.3 to 2.4, we'll be looking at graphing of your data. So in the next 2 chapters, we'll really be looking at differing characteristics of the data, the shape of your data, the distribution. So we'll be looking at the distribution of data, the distribution, and in this chapter, we'll be looking at it graphically. In later chapters, we'll be looking at it mathematically. There'll be that your particular distribution will satisfy some mathematical formula. We'll be looking at the center of the data, some way to represent what is the center of your data. These will be called the measures of central tendency. These will be in general numerical. That'll be in chapter 3. So that will be the first time we'll really be doing any sort of mathematical calculations. We'll be also looking at the spread of your data. What's the variation of your data? These will be called measures of dispersion. Again, these will be numerical. And so we'll be using some mathematics to look at these quantities. Next. Well, these quantities, actually shape, center, and variation, will be greatly affected by outliers. So we'll need to discuss outliers. An outlier is something far away from the vast majority of everyone else. And so if you're way, way far away from everyone else, we call you an outlier. And well, we'll be looking, but it'll be a very minor. I think that what happens over time, we'll be more worried about this like the very last 2 chapters of the course. So not now, but well into the future. So if you've ever looked at a gigantic list of numbers, let's say you have 1 million numbers, and you look at them, and they're not in any order, and they're not organized in any manner. They're just all listed one after another. Human beings, when they see this, they see nothing. It just looks like garbage, gibbery, just nothing you can tell what's happening. It's just, gibberish. They can't figure out what's going on at all. And so, how do we deal with that? Well, we will give it first a frequency distribution. So, if we look at, well, what is a frequency distribution? A frequency distribution is a set of ordered pairs where X is the value of your random variable, and F is its corresponding frequency of occurrence for this particular random variable. If you have a lot of these, then it still is gibberish. You can't figure out what's going on. So we will instead look at a group frequency distribution where it's still sets of ordered pairs. But this X here will not be a random variable, but a range of values, a class interval, an interval of values, or just a class. So we have some X, the class, followed by F, the frequency of your random variable being within this particular class. So first, let's look at a frequency distribution. Then we'll look at a group frequency distribution. So suppose I have the following set of raw data, and we want to organize this data as a frequency distribution. So I have here 2, 3, 3, 4, 4, 5, 5, 5, 5, 6. So I write down here X and F. For the X's, I look, well, what are the values that X can take? 2, 3, 4, 5, and 6. So 2, 3, 4, 5, 6. Next, there is 1, 2, 2 3s, 2 4s, 4 5s, and 1 6. And so I can organize this raw data as a as this frequency distribution. You can also do it in Excel. Using the COUNTIF command. To organize this in a frequency distribution, I would do the following. So it's 1, 2, 3, 4, 5, 6. So I have here, there's a 4, a 6, a 1, a 6, oops. A 3, 3, 6, 5, 3, 5, 4, 3, 5, 6, 3, 6, 1, 1, 5, 4, 5, 4, 3, 6, 1, 3, 1, 6, 6, 4, 5, 2, 5, 4, 4, 4, 5, 1, 3, 6, 2, 4. Okay, so I have 6, 2, 7, 9, 7, 9. Okay, so let's add these up. Let's see if I have the correct amount. 18, 25, 30, 40. And I rolled it 40 times. Good. I always check to see, because I'm never sure that I added these up correctly. And so if I do that, I have the following frequency distribution. So You just go in a systematic fashion and count up everything. So my frequency distribution looks like this. Of course, you could also just have done Excel. It would have been just as easy. Now, what if your frequency table has a lot of different categories? So if all of a sudden, it's, let's say you have a million, your raw data is 1 million data, and it takes on 10,000 differing values. Well, then your frequency distribution would have like 10,000 values, 10,000 ordered pairs in it. That's too many ordered pairs to figure out what's going on. So we use a grouped frequency table. So use a group frequency distribution when the number of values of the random variable that are changed is greater than 25. So if you have more than 25 different values that can be attained by the random variable, then use a group frequency distribution. So this is an example of a group frequency distribution. So I have here F, your frequency, X for the class interval. So there are 5 numbers between 10 and 20, 3 numbers between 20 and 30, 2 between 30 and 40, 3 between 40, 50, 2 between 50, 60, 3 between 60, 70. The smallest numbers here are called the lower class limits. So the lower class limits are the smallest number in the class intervals. So for the class 20 to 30, the lower class limit is 20. Okay. Next. Oh, so I should tell you this. The class limits should have the same decimal place as the data. So if your data are whole numbers, then your class limits are whole numbers. If your data was up to the nearest 10th, then, well, the class limits should also be to the nearest 10th. So the upper class limits are, well, the largest numbers here. So 20, 30, 40, 50, 60, 70. So for the class 20 to 30, the upper class limit is 30. The class boundary. So the class boundary is the upper class limit of the preceding class plus the lower class limit, all divided by 2. So the upper class limit is the upper class limit plus the lower class limit of the preceding class, all divided by 2. The class mark, sometimes called the class midpoints, are the upper class limit plus the lower class limit divided by 2. So let's say in the interval 50 to 60, 50 plus 60, 110 divided by 2 is 55. So the class midpoint, the class mark for the class 50 to 60 is 55. The class width is the lower class boundary minus the previous lowest class boundary. I should really say the upper class boundary minus the lower class boundary. That's actually, yeah, that's the way it should have been stated. Sounds like, looks like a G. So the class width is the upper class boundary minus the lower class boundary. Equal class width. If all of your classes have the same class width, then we say that this has equal class width. And open-ended. So sometimes you see the following, where it says 60 or greater. So maybe there are 3 numbers that are 60 or more. Or you could see, you would have it on the other side, where it says 20 or less. So maybe there are 5 numbers that are 20 or less. If either of these happen, then we call this a open-ended frequency distribution, group frequency distribution. So either the lower class interval has no lower class limit, or the upper class interval has no upper class limit. Now, there are 2 different ways to do frequency distributions, group frequency distributions, either exclusive or inclusive. So I could have written these as 10 to 69, 70 to 89, etc. Or I could have written these in this fashion: 20 to 30, then 30 to 40, etc. Now the question is, well, what does this mean? So, oh, I just saw this. Wait 1 second. And so the question is, like, so what do these mean? What if I had the number 30? Would the number 30 be in this interval or in this interval? Would it be in both? Well, let me give you an example and you tell me. So what did I say before? 85 to 100 is an A. 70 to 85 is a B. 55 to 60 is a C, to 70 is a C. 40 to 55 is a D. And 0 to 40 was an F. So I'll ask you, I got an 85. What grade do I get? Well, let's see what people say. If I got an 85, what do I get? So anyone? What do you get if I got an 85? An A. Yes. Person says A. Of course, I want an A. Meaning that, well, let's say for, and suppose you got a 70. What grade do you want? What grade should you get? What grade would you demand? You would demand that you would get a B. Meaning that if I look at this interval, that really means that 70 to 85 means that, well, if X is between 70 and 85, well, I should get a B, meaning that if I got a 70, I still get a B. But if I get an 85, I don't want a B, I want an A. I want it to go to the next class. So this is what it means. It's easy if you think about grades. That's what you want it to equal. Therefore, for, and these are called exclusive type classes, when the class limits are the same as the class boundaries, then say 10 to 20 means X is between 10 and 20. You include the 10, but you do not include the 20. Look at grades. You had no problem with grades. You knew exactly what to do. That's what you do with in any other situation. Okay. So we use these in physical sciences. And this is because, well, the mathematics is easy. We're lazy. We don't want to do something that gives us more mathematics to do. So we will be using these in this class. So in general, when I do examples of this type. Only occasionally will I do inclusive type classes. So an inclusive type class, let's say we write the class 10 to 15. So in this case, what it really means is look at the class boundaries. So this actually means 9.5 to 10 to 19.5. We include the 9.5, but not the 19.5, just like above. So to me, there's no real benefit for writing it this way. It just makes your life harder. Makes all the mathematical computations more difficult. So I don't see an advantage in this. It is used in the social sciences. In general, the mathematics is difficult. So usually in the social sciences, they don't care about the mathematics because they don't do the mathematics. So they don't care if the mathematics is difficult. So again, the class limits should have the same decimal place value as the data. But the class boundaries have one additional place value. And they always end, the rightmost digit is always a 5. So let's look at this. In our example here, five numbers between 10 and 20, 3 between 20, 30, 2 between 30, 40, 3 between 40, 50, 2 between 50, 60, 3 between 60, 70. The lower class limits are the first numbers, 10, 20, 30, 40, 50, 60. The upper class limits are, well, the second numbers, 20, 30, 40, 50, 60, 70. The class marks. Well, actually, let me look at the class widths first. So to find the class width, I'll just subtract. $20 minus 10, 10. 30 minus 20, 10, etc. For the class marks, I'll just find the average. 10 plus 20, 30 divided by 2, 15. 30 plus 50, 30 plus 20, 50 divided by 2, 25. Notice I could have also done, well, so to find, like, let's say the class width, I could have done 25 minus 15, 20 minus 10, 20 minus 10, 30 minus 20. All of those would have given me the same answer. So there's a variety of different ways to actually do these calculations, all of which are kind of easy. So it's nice to be able to have several different ways, because maybe one of the numbers is easier than the other. Next. IQ scores of low lead. And so we'll be using inclusive type classes. 59, 50 to 69, 70 to 89, 90 to 109, 110 to 129, 130 to 149. So the lower class limits, well, are those lowest numbers that are shown. 50, 70, 90, 110, 130. Upper class limits. Well, those are the biggest numbers shown. $69, $89, $109, $129, $149. Class boundaries. Well, let's do this. 69 plus 70 divided by 2, 69.5. 90 plus 109, 199 divided by 2, 89, etc. Let's do the class midpoints. And so 50 plus 69, 119 divided by 2, 59.5. 89 plus 70, 159 divided by 2, 79.5, etc. Class width, well, 70 minus 50 is 20, or you could do the $69.5 minus the 49.5. This still also give me 20. Okay. What constitutes a good group frequency distribution? Now, these are just sort of general rules. They aren't really applicable in all cases. So this is your goal. It does not mean that these are actually things that are the best practices for any particular situation. So there are many situations where this doesn't work. So this is just sort of a goal that should be achieved if possible. Your number of classes should be between 5 and 25. I always say use exclusive type classes. They should be mutually exclusive, continuous, and exhaustive. So mutually exclusive means that if you have a piece of data, it goes only into one of the classes. So there should be some rules that tell you that this is the particular value that goes into, this is where this particular value goes into. And so you should be able to determine your class interval for any particular value. Next, there's no gaps. So even if you have that in a particular region, there's some, maybe there are no values between A and B or something. You still have to use that interval. So even if there are none there, you're still going to have to keep it there so that the classes are continuous. Next, not to be exhaustive, meaning if you have a data value, it has to go somewhere. And so you have to have enough classes so that all of the values are able to be put somewhere. And if at all possible, classes should have equal class width. Sometimes you might need to make this into a open frequency distribution. So you might need to either have the upper or the lower classes as being open-ended. So in general, there's no way to guarantee that all of these are satisfied, nor that all these, well, you can always guarantee that all these are satisfied, but it could be inappropriate for all these to be satisfied. So one easy sort of technique so that most of these conditions hold for many differing types of raw data is Sturge's rule. So Sturge's rule says K, which is the number of classes, is equal to 1 plus the log of n divided by the log of 2, where n is the sample size. The idea for the Sturge's rule is as follows. If you have only one number, so if your class size is just 1, then you should only have one class. So K should equal 1. So if n is 1, K should equal 1. Next, if you double how many numbers there are, then you should add one additional class. So you have one number, one class. Two numbers, two classes. Four numbers, three classes. And you keep going by doubling each time and adding one additional class. So let me do an example. Let me not explain the algorithm. So there is an algorithm here. Let me try to explain the algorithm with a particular example and hope that that clarifies what the algorithm is. So suppose I have the following set of raw data. 10, 11, 14, 15, 16, 20, 22, 28, 31, 35, 45, 48, 50, 55, 56, 68, 69, 71, 71, 73. Okay, so now hopefully take out right now your calculator. So you should always come to class with a calculator. So find your calculator, where you've stored it, and do the following calculation. The reason I am insisting that you do the calculation is because this is a source of error that students have, that they can't do this calculation. So I want to find K. Remember, K is the number of classes. So I want to first figure out the number of classes. Again, using Sturge's rule. 1 plus log n over log 2. So I have to figure out n. N is the sample size. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. N is 20. Plug this into your calculator. See what you get. Question?
Yes,
So-
I do have a question.
Yes.
Yeah, so the log, is it gonna be log 10 to the 20 or?
Oh, are you asking? Should you use log or ln? Is that what you're
Yes.
asking? Don't care.
Okay.
Why? Because it gives you the same answer. So in the formula, it's actually base 10. So you should use a log base 10. But actually, if you don't, you still get the same answer. So it turns out you get the same answer. It's the proper rhythms. You can do that for fun, but you'll see that you get the same answer. So if you're using a TI-83, it'll be 1 plus log, notice the parentheses, ends, 20, and you end your parentheses, divide log of 2. So you need to end your parentheses first for the 20, or for the 20, the log that involves 20, or you'll get the wrong answer. Let's see how people are doing. Any problems with doing this calculation? New problem. Is everyone done with this? Did everyone get that answer? Did anyone not get that answer yet?
Or confirm the same answer.
You got the same answer? Okay.
And I used the natural logarithm. So.
Oh, you use the natural one. Yeah, you notice you got the same answer, right?
Yeah, because it's log 20 over ln 10. And
Yeah, so even if you use the other logarithm, you'll still get the same answer. Okay, so now I'll assume that everyone got it. This is a common source of error that people cannot do this calculation, but I'll assume that you've gotten it correct. Now let's figure out the class size. And so, the class width. Let's figure out the class width. So H here is, well, let's see. Actually, let me say that, how do we do this? So we figure out the range. So what is the range in this case? Well, we go from 10 to 73. So the range is, well, 63 to 73 minus 10. And I divide this by the number of classes, the 5.321928,095. So do that on your calculator and see what you get. Hopefully you get your 11. Let me wait a second. Okay, everyone got it?
Yes.
Yes, okay. So
But do
Now
we
the
have to
problem
full, to divide by the full decimal places? Does it have an impact?
say again.
Do I have to divide by the full decimal places?
Yes.
5.3219?
Yeah. Do the whole thing out.
Okay.
It's better to write everything out. And then at the end, so I'll always just say write everything out because there are different ways to approximate and to truncate your answer. And everyone will do it differently, and every major does it differently. So because of that, I won't specify any techniques because I won't know the exact technique that your instructor utilizes. So I'll just say write everything out. But now the question is, well, K here is the number of classes. Can you have 5.32 classes? Can you divide this into 5.32 parts? No, in other words, I want to find a class, right? And I want, well, this number of them. I can't have a fractional number of these classes. So that's a problem. That's why we have this algorithm here. And why I'm going to be doing this example to sort of make you, hopefully have you understand what this algorithm is and why it proceeds. So H here is the class width. Now, the class width should have the same number of, well, it's somewhere, I said it's somewhere. It should have the same number of decimal places as your data. The data are integers. They're to the whole number, to the unit decimal place. And so your class width should be an integer because that's what your data is. So now the question is, well, how do I do this? Well, either I can round this down or I can round up. So I can either say, well, it's either 5 or 6. So this number is somewhere between 5 and 6. And this number should be somewhere between 11 and 12. So both of these are going to feed off of each other. So I'll look to see what happens when I round this down to 5 and round this up to 6, and what happens when I round down to 11 and round this up to 12. So now, if I look here at a group frequency distribution, such as this one, which is more work, just making these wider or having to add an additional class? Well, having to add an additional class is much more work than just changing these guys. So changing this to be bigger, to go from 5 to 6, adds more work than changing this from 11 to 12. So our algorithm says, well, the first thing that I'll do is try to take 5 classes of with 11. See if that works. If that doesn't work, do 5 classes of size 12. If that doesn't work, well, the 5 classes doesn't work. So do 6 classes of size 11. Then 6 classes of size 12. One of those is going to work. And so one of them is going to work. Figure out which one works. And if you do it in that order, it'll be the preferred one will be the first one that works in that. So first, I will let K here equal 5. And then I will let H here equal 11. And let's see what happens. Well, if you have 5 classes, 1, 2, 3, 4, 5 classes of with 11. Well, where do we start out? We start out at the smallest number. So start out at the smallest number, keep adding 11 until you have 5 classes. You want that to end so that you can include all your numbers, so that the largest number, the 73, is less than or equal to the 5th of these classes of with 11. Well, but in this case, notice the 65 does not include all these numbers. And so something goes wrong. If you look here, how did we get 21? We added 11. How did I get 32? I added an additional 11. Keep adding 11. And so we want that the maximum here should be less than or equal to the smallest number plus h times k. So let's do this. So now our algorithm is as follows. We start with where we truncate both h and k. So truncate h and k, meaning get rid of all the decimals. So get rid of the decimals. So just 5 and 11. Then check if the minimum 10 plus 5 times 11, 65, if that is greater than or equal to your biggest number, 73. Well, it's not. So keep going. So now let's do the next one. Let's make h larger. Let's round up. Let's round up h. So if you round up h, then you get 10 plus 5 times 12, that's 70. Again, doesn't work. So now that means that we can't deal with 5 classes. Let's go with 6 classes. I start at the smallest value for h. So h in this case is 11. And so 10 plus 6 times 11, 76. Good. That's greater than or equal to 73. And so we should have 6 classes of class with 11. So we start with 10 plus 11 is 21, plus 11, 32, plus 11, 43, plus 11, 54, plus 11, 65, plus 11, 76. And then oh, I can't. Then we see how many numbers. I'm going to do it this way. Oh, here it is right here. There. Okay. So now I'm going to look. So 10 to 21. How many numbers between 10 to 21? 2, 4, 6. So there's 6 numbers between 10 and 21. How many between 21 and 32? 3 numbers. 32 and 43. 1 number. 43 and 54. 3 numbers. 54 and 65. 2 numbers. 65 to 76. 5 numbers. And so this is my group frequency distribution utilizing Sturgeon's rule. Okay, so let's use our frequency distribution to understand data. So let's see if I can somehow think about look at a frequency distribution and see if I can figure out what's happening. So many times the distribution has a bell shape. If there are gaps, then it could be that the data is from 2 or more different populations. So if we have some sort of bimodal distribution, that could indicate I have somehow 2 different populations I'm looking at. So let me show this. So the table below is a frequency distribution of randomly selected pennies. You can actually do this with pennies. It's actually quite interesting. And actually, if you are not able to weigh a penny, you flip a penny like on, concrete or something, and you listen to it. So take arbitrary, hopefully you have like 30 or 40 pennies around and flip them. All of a sudden you'll notice some of them have, well, I shouldn't say this. Okay, so let's look at this table below, a frequency distribution of randomly selected pennies. So we're going to look at some pennies, discuss what the distribution of weights of pennies might tell us. So 2.4 to 2.5, 18. 2.5 to 2.6, 19. 2.6 to 2.7, 0. 2.7 to 2.8, 0. 2.8 to 2.9, 0. 2.9 to 3.0, 2. 3.0 to 3.1, 25. 3.1 to 3.2, 8. So now, what's going on? Why is this happening? So tell me. So if you look, it looks like, so it's 18, 19, 0, 0, 0, 2, 25. Oops. 25, 8. So that's what my distribution looks like. That's kind of weird. Why would it look something like this? So why does the distribution look like this? Anyone? Does anyone know? Can anyone think of why would that happen? So why would pennies look like this? A whole bunch of pennies between 2.4 and 2.6. Whole bunch of other pennies weighing between 2.9 to 3.2.
They sound if they are split from one coin.
Well, say it again.
They sound as if they have been split from one coin in half. So one gain and one lose.
Okay. Actually, someone said here, different metals. And that's correct. They're actually done with different metals. So, right, if you actually look at a penny, I don't know if you've seen a penny before, but you look at the side, if you look at the side of a penny, all of a sudden, pennies are, so a penny is copper. It looks like this copper color. But if you look at it sideways, it doesn't look, it looks like a different color, of metal. And that's because actually pennies are no longer, so these are made with copper. So the old coins were made with copper. The newer coins are made with zinc. And what they do is they fool you. They just plate them. So these are plated with, so it's zinc with a copper plate. So all they've done is they just sort of painted the front and back of it copper. They put a very, very thin layer of copper on it. And the reason for this is that copper is too expensive, too much money. So copper costs too much. And so it costs much more than a penny to make a penny. So they then changed to zinc. And unfortunately, zinc now pennies still cost more. So they did this so that they could cut down on expenses. But zinc here actually is too expensive. So I don't know if you've noticed the last few years, but they have been saying that they are actually going to stop making pennies. So now the problem is that, so the real problem is that they said something like 99.9% of all pennies are not in circulation. So the real problem is that the government is spending money to make pennies, and each of these pennies costs more than one penny to make. And when people get pennies, what they do is they stick it in their pocket and then they throw it in a drawer. They just never put them back into circulation. And unfortunately, I know people who do this. They flush them down their toilet. And so they just flush pennies down toilets. And of course, that produces horrible consequences for the sewer system because with all these excess pennies around. So there have been many discussions where we're going to get rid of pennies because of this. So now here it is right here. That tells you right now. So pennies made before 1983 were 95. So I forget when I think it was in the 1950s. It used to be 100% copper. And then, but you have to have really old coins. You're not gonna see much of a difference here. It just weighs slightly less, slightly more if you get a real old copper penny. So before 1983, it was 95% copper and 5% zinc. After 93, it is 2%. See, it's really no longer copper. It's 2.5% copper and 97.5% zinc. So if you flip a coin, if you flip a penny, if you flip an older penny, it has this like thud. Whereas when you flip a coin, a new penny, and it hits the ground, it goes ping. It has this much higher frequency that you can hear. So you can tell, wait, this is not the same made with the same metals. So it's 97% zinc. So a copper penny is really a zinc penny. So really, these pennies are now zinc because it's cheaper. So again, this is cost saving. So, but unfortunately, now the whole process now costs much more than a penny. I think it costs like, I don't remember. It's approaching 2 to almost 3 cents, I think, for every penny. So they really don't like pennies at all because they just cost too much to make. And the fact that people don't use them. But even though it costs too much, people don't like when the government says they're not going to produce pennies, just because then, I don't know, then they're afraid that everyone's going to raise prices when they round up to the nearest nickel. Okay, so reasons for constructing frequency distributions. Large data sets can be summarized. We can look at the nature of the data. We can construct important graphs from it, organize data in meaningful ways, look at the shape and nature of a distribution. It will facilitate computational procedures for the average and spread, and being able to draw graphs for presentations and to compare different data sets like we did in the last one. I see that our time is up. We're done.